Today we're going to talk about Appalachian and New York geology. So we're going to kind of give the geologic story of the rocks that we see on the field trip and also those that we see around New York City. So we'll start out by sketching the just kind of the eastern U.S. So this is Florida. Not drawn very well. I'll try that again. So Florida coming up. There's like Long Island. And we got Maine up here. Okay. So New York in this area. And the Appalachian Mountains can be represented on here as a series of thrust faults. So we'll put teeth on these. And that belt of deformation extends for quite a ways, where it gets covered up by so we'll draw this sort of getting covered by, in this area, late Mesozoic and Cenozoic coastal plain. Okay, but we can see this kind of continues again on the other side here in the area of Texas. So we call this part of that belt the Ouachita. Ouachita, Ouachita orogenic belt. Up here, we call it the Appalachian. Actually up here and all the way down along the East Coast. And it continues, we can put a little arrow there. It continues into Greenland and Scandinavia. So Scandinavia. So it's clearly, this is a feature that predates the opening of the Atlantic. Okay, so that belt of deformation cuts across another boundary, or a couple boundaries actually. So we'll draw so we have a younger boundary here, which is the Paleozoic Platform. So platforms and plains are these kind of like pretty thin layers of sediment associated with relatively high sea level covering parts of the continent. And then the Paleozoic rocks overlie 1 billion year old, roughly, Grenville. Orogenic belt. And that has a sort of a thrust relationship with 2.4 billion year old Superior province. And we can see that this suture, this boundary between these two really old Precambrian zones, existed and continues underneath the sediments that were deposited in the Paleozoic. So all this area here is what we call the craton. So it's like, this is like the really old parts of North America. So it's probably worth just to, let's put a timeline here, Earth history, just to refresh that on that. Okay, so we can start down here. So 4.5 to 2.5. 2.5 is the Protozoic. Archaean is the really old stuff back from the Earth forms. So Earth forms here. We've got a couple billion years till we get to the Protozoic. We start to see sort of more obvious signs of life. About 0.5 of the Paleozoic. And 0.25 Mesozoic. These are really rough. 0.065 Tertiary. So Mesozoic, of course, dinosaur time. Paleozoic, recognizable life. For example, animals. Protozoic had some sort of algae, that kind of stuff. Okay, so just relating that over here. So Paleozoic Platform. Okay, so we'll be backing up even further. So 2.41 billion years. So these age rocks are back here in the sort of Proterozoic time, before really much, recognizable life forms. The Paleozoic Platform is occurring, there'll be plenty of fossils and shells and that kind of thing in these rocks. And then this coastal plain, so these sedimentary rocks that overlie the Appalachian mountain belt, occurring during the time of the dinosaurs, since then. All right, let's make a little bit more room here and just define a couple things that words that we've tossed around. So craton, we've talked about this before. Craton is stable crust, so it formed and then it's experiencing little deformation. Or metamorphism. For long periods of time, greater than a billion years. And then the other word that we used, we'll get that down, platform. These are flat-lying, thin, sedimentary rocks on the craton. Okay, so right away you should, when you're looking at this map, you could start to make in your mind, I'd encourage you to pause the video for a minute and just kind of think about sequence of events. Like, what is a geologic story? Make this huge map of Eastern North America. What is this map telling us in terms of the geologic history? So think about that for a minute, and then we'll continue and kind of tell you the answer, more or less. Okay. So the other evidence that we want to sort of, before we get to the geologic history, the other sort of key information that helps us understand geologic history is diagrams of the sedimentary rocks that are sort of, you go around, you measure their thicknesses, other characteristics about them, and these can tell us a lot of information about the geologic history. So this will become a little bit, so this is the diagram that's going to go from the northwest, say Ohio, to the southeast, let's say Virginia. So it's a summary of a lot of work by a lot of different workers. And we'll shade these to kind of make them a little bit clearer. So this one is shaded. So the thicknesses here are important. These are the thicknesses of different packages of rock. Okay, and then we're going to do another one. And then one more. Okay. So the shaded, let's make a little key here. Shaded is clastic sedimentary rocks, and then unshaded is carbonate. And let's just label this diagram Eastern North America stratigraphic section. And then we're going to have another thing in our key here. That a little arrow is going to be the sediment transport direction. So this is the direction. You can look at the cobbles like in the sedimentary deposits and figure out, oh, the water was flowing this way or that way. So these clastic sequences, you can tell that the clastic just means that they have it's sand and clay and conglomerate. These tend to happen when there's kind of more geologic action, whereas the carbonates occur when the weather's warm, and they tend to accumulate at a slower rate, just based on the kind of slowly occurring accumulation of life, corals. So put some. So under all this is basement. So put some little X's indicating like high grade granites and gneisses and that kind of thing. Okay. So we're going to number these And then when we go through the geologic history, we'll kind of come back to these numbers. Okay, so one, the oldest rocks here that with sediment flowing from the northwest towards the southeast. This is Lower Cambrian. So Cambrian is the first time part of the Paleozoic. So Lower Cambrian to Precambrian. Clastic sequence. On top of that, we have, I'll write it in here, Cambrian to Ordovician carbonate. And this accumulated, we can figure out how quickly it was accumulating, about 10 to 20 meters per million year. And then on top of that, we have another of these clastic sequences, but the direction of the source, basically, like if you've got a big mountain range nearby, over here the mountains are going to be to the northwest, transporting down to lower lying land. Here the mountains are more in the southeast. Same thing here, okay? So these rocks here, we can put both a 3 and a 4. These are, we should label this one too. These are Ordovician to Silurian clastic. And these accumulated a lot faster. So these were accumulating at an order of magnitude faster, 200 to 300 meters of sediment per million years, what we see. So clearly something, there's an event indicated by the carbonates just getting buried in very rapidly in sediments. So these, one of the rock types that we see on the field trip, the Ordovician Austin Glen, is part of this sequence of clastic materials. This is a sandy and muddy rocks. Here we have Silurian to Devonian carbonate. These are the field trip rocks. So most of the rocks, the carbonates that we see on the field trip in the area of Catskill are Silurian to Devonian carbonates. And then on top of those is some more clastic material, Devonian clastic sequence. All right, and we'll come back to this as we go through these, the sequence of steps 1 through 6. Okay. All right, so the next is going to be a series of cross sections. So we start out with a craton. And we deposit sedimentary rocks on it. Okay, so this is what when we talked about a passive margin in a previous lecture. This is a passive margin. It's early Paleozoic. Stable continental margin. So just going back for a second. Early Paleozoic. That's this stuff over here. So we had a craton, this older stuff, is where we're going to start the story. Even though there clearly was an event that at about 1 billion years that plastered the Grenville rocks onto the previous core of the continent. We're going to start with, we start with, okay, since 1 billion years, we're just going to start by depositing, this event happened, then we deposit a passive margin on top of it. And that's the first, in this sequence here, that's this first layer of rock sitting on top of the crystalline rocks that existed previously. Okay. All right, and then the next step in the process here we have those sedimentary rocks from before, the craton, and the temperature is warm, we're near the equator at this time. We deposit carbonate on top of what's there before. So the water level is relatively high. So the water level is pretty high. It's kind of like the modern Bahamas or Florida. So let's continue drawing the ocean crust out here. Eventually, far enough out in the ocean, there's a subduction zone. So we've got the ocean. An island arc. With its accretionary wedge. So an accretionary wedge is just the as the subduction occurs, so some of the sediments that get scraped off, and you get this kind of wedge-shaped mess of sediments. And you could say paleo environment, like present-day Florida. So eventually, this ocean is shrinking. As this plate is subducted, this island arc gets closer and closer to the continent, and our next event, 3, looks something like this. So we have our sedimentary or carbonate sequence here in our craton. So here's our craton rocks and our carbonate sequence getting folded. as a result of this so let's draw that a little bit up. This island arc here. And this would be a thrust fault, and there'd be other thrust faults occurring. Deep underground here, there's maybe folding. And this is all this activity here is going to shed sediments into a basin. So this stage, and this would be the rocks like the Ordovician Austin Glen that we'll see in the trip. So we could title 3 Deposition of Austin Glen and related rock layers. So let's just go back and look at the sort of stratigraphic column. So what we've come up through here 3. So we started out with this passive margin sequence here. Put some carbonate on top of it that deposits fairly slowly. And notice how the direction of sedimentation has shifted. So earlier on, we were shedding, if this is northwest and southeast, we go up here, sort of northwest, southeast. So this area that had experienced mountain building previously, sediments are coming from it towards the southeast as part of this platform. And then when the island arc hits along the coast here, this area of the east coast suddenly becomes the high area, and sediments are moving from the southeast towards the northwest. So we see, we deduce this story by looking at this evidence that you're looking at here. So we see that there's a change in the direction of the sediments. We think, oh, well, there must have been activity to the east, right? So we've now buried the carbonate in classic material that's sourced from the east. So we could put those same directions up here as well. Might help. Okay. So now we see where the tectonic environment where the Austin Glen was deposited. And we went from Austin Glen is a fairly deep, deposited fairly deep. So collisions like this can actually push down. These carbonates are formed right near the surface of the ocean, very shallow water. Collision can push down the rocks and make for a deep basin. Okay, so following deposition of the Austin Glen and related rocks, well, actually, before we draw another picture, let's just kind of describe what the Austin Glen is. Austin Glen is a rock called a flysch. So a flysch is dark, typically dark colored, typically fine-grained, thinly bedded. Sandstone, shales, clay. So you might remember the Austin Glen fits this description. Flishes are often deposited by something called turbidity currents. In deep water. Also often deposited in small basins. During early subduction or collision. So this type of rock, this sort of tectonic association of rocks called flysch. So the flysch was originally described in the European Alps, and then subsequently it's become recognized that these are found worldwide, and they're often associated with these kind of basins right at the beginning of a collision. And the fairly deep water. Turbidity currents are a type of sedimentation where water gets mixed up with mud and other fine-grained sediment, and as a mixture, it has it's denser than normal water, and it can kind of slide down a slope as a result of its larger density. And so that's one way you can transfer sediment very large distances. Okay, so let's move on now to the next step here. Okay, so 4 we'll title collision or continuing collision. Collision, tilting, thrusting of Austin Glen with North America. Okay. So we're continuing to put the island arc, jam it onto North America, and so subduction has stopped. We don't really know what's happened to the subducting slab down there, but we've crammed down in here those carbonates that we deposited before. These are buried deeply, metamorphosed, folded. Parts of the Austin Glen that are that were deposited now are so here's some of our Austin Glen. We're gonna be folding it, thrusting it. It's going to be tilted. You can imagine little, there's going to be folding associated with this. And that Austin Glen, these layers also are getting pushed down underground, developing cleavages and high temperature metamorphism, folding. And we're also going to put something called an ultramafic rock. So there's Craton. Okay, so this dark stuff is ultramafic. So this means it's very dense, very dark rock. Ultramafic is generally former ocean floor. So this stuff kind of marks the boundary between, so we could shade this. So this ocean crust, let's make it dark. Okay, so this island arc is going to collide with North America with this cratonic stuff. And a little bit of this ocean floor is actually going to get, as they collide, it's going to get, we could put some in here as well. Shade this ocean crust there. It's going to get kind of scraped off and stuck between the two parts that are colliding here. So we find a little bit of this ultramafic separating the old North America and this part that's being added on. So let's just describe what's happening here. We have high grade metamorphism. Oops. High grade metamorphism. Oh, that was what I want to do. And folding. Ordovician sediments, which are getting turned into what we now know as the Manhattan schist. So there's a connection between the rocks that we see in the field trip, which is like this stuff over here, and the same material with the same age, roughly, that suffered a different fate, was actually jammed down, buried underneath the island arc, and folded and highly deformed and metamorphosed. So this is what we now know as the Manhattan schist. Okay. Parentheses here. So actually, let's go back. All this, so this was stage 4. So this is occurring roughly at this time. So we're not really depositing much. This is a time of erosion. This would be a time to form an unconformity. We're pushing things up, burying things. Next, we'll move on to 5, which is this is when the rocks we see on the field trip are going to be deposited, or most of them. See that we see some of this a little bit, and then most of what we see is this carbonate. So where does that come from? Let's show that next. So actually, we could call this, let's label this further. So 4, we call this the tectonic orogeny. And then 5 would be post-tectonic orogeny. And what happens at this time? The tectonic mountains erode. So you can imagine that during this kind of event where we have we're thrusting all these things on top of each other, you're going to build topography, you're going to build a mountainous terrain. So the tectonic mountains erode. In the Silurian, sea level rises, and this happens globally. Plus, there's also probably some tectonic related uplift. And this is going to flood the eastern New York. So it's going to flood and form an unconformity surface. And then carbonates are going to get deposited on that. For example, those that we see in the Catskill area. So these are deposited. So, in other words, we formed the tectonic angular unconformity. And let's draw that. So we have, basically we're gonna deposit carbonates, another set of carbonates on top of what was there before, which was quite a bit of stuff. This high-grade folded clastic rocks, folds, thrust faults in the Austin Glen and other rocks that were exposed to the surface. So this boundary here is the tectonic unconformity. So the next stage, 6, is the Devonian. This is around 380 million years ago. Devonian Acadian orogeny. So at this time, a continent fragment. So we often think of continent collisions. Oops. We often think of continent collision like India-Asia. It's like, oh, big continent crashes another one. But it turns out that a lot of times the Indian-Asian collision actually is this. India is just the last of many little slices, kind of Madagascar size and shape, bits and pieces that collided with Asia over time. So a similar fragment of continent collided with North America. And this caused, among other things, faulting and folding in the Catskill area. And actually, this was one part of a series of collisions that together formed supercontinent Pangaea. So kind of in the same way that if we keep adding India and other things onto Asia, we're eventually going to create a supercontinent. Okay, so now we take our unconformity surface that we formed previously and do all kinds of crazy stuff to it. Okay, so those carbonates that we just deposited now are going to be affected by this collision. They're going to get folded, faulted. There's a fault, there's another fault, thrust faults. The unconformity itself is getting folded. Basement, so the underlying rock, so this involves like all kinds of stuff. Everything we've drawn before is under this unconformity. And there's basement, there's the Ordovician sediments. That stuff is also gonna get pushed up. It's also gonna get pushed down, folded and metamorphosed. These same carbonates here are getting buried and folded and metamorphosed by, so we can kind of imagine this continental fragment that's collided with North America doing this. Let's go back to this diagram. Okay, so here we see, okay, as you would expect, when this kind of when there's collision, we put down classic sedimentary rocks. There's a lot of erosion. That stuff ends up. It's a collision in the east, which is going to cause the sediments to get sent to the west. You can imagine further distances that there's going to be less sediment. Very near it, it's going to be thicker. So that's why all of these packages kind of have this increasing thickness to the east, or that's part of the reason. All right. Okay, the next thing that's going to happen that's not really represented on that strat column, though, around 200 million years ago, Pangaea. So we've made the supercontinent Pangaea by colliding things together. Pangaea is going to break apart. Pangaea breaks apart. Atlantic Ocean forms. So you can imagine, we're not going to draw it, but you can imagine now on top of this, we're going to put another passive margin. So this cycle, this would be like, I guess if we go back to this map here, so these sedimentary rocks would be part of that. So this cycle of collisions, getting eroded away, sediments depositing, oceans, more collisions is continuing. So actually, let's go back to this section here, and we can add a bit to it. So in this column, we've written some sort of the field trip related rocks in the New York City area. These rocks are also represented. So the Inwood marble is metamorphosed carbonate. So Inwood marble is the same stuff. As I said, the Manhattan schist is the same as this similar age and same starting material as this Austin Glen material. Underneath the inward marble, there's a quartzite. And then, continuing that, is rocks called the Fordham and Yonkers gneisses. And ultramafic rocks. Represent this time period. So the same sequence that we see upstate, we see the metamorphic equivalent in New York City area, and that's because of basically this. These rocks are formed. Some of them to the southeast are pushed down and metamorphosed. Some of them remain pretty close to the surface and don't really experience much in terms of temperature and pressure. So we'll wrap up with New York today. So New York looks something like this. Okay, up here we have high-grade stuff, folded rocks. This is the Adirondack mountains. These are part of that 1 billion-year-old province. Overlying that is the late Paleozoic platform that we talked about. Lake Ontario would be here. And then we have a sequence of thrust faults and deformation, including something called a thrust sheet. These come all the way down to something called Cameron's line. Which is related to those ultramafic rocks. And we've got Long Island. So the ultramafic rocks, again, are former ocean floor. And everything that I've kind of shaded here is related to that island arc that collided. So the island arc that go back, that caused the tectonic orogeny. So this island arc here colliding. So now we kind of have this boundary between the old North America stuff and then the stuff that got plastered on. So that Cameron's line is the boundary that separates those two things on the map today. And this really, I didn't really do a great job at this. This Cameron's line kind of cuts through New York City. Okay, so that's an overview of the tectonics of New York and Appalachians. And hopefully gives you some idea of how we relate the geologic, how we take basically our observations. We look at the map, we see these different kinds of rocks in different places. We figure out how how hot they were, or how deeply buried, or how folded, and we interpret this story based on those observations.